Welcome to this explainer. We're jumping straight into a truly radical mathematical breakthrough today. We're talking about a fundamental shift that actually solves the massive energy drain of modern AI, literally by changing how we calculate geometry itself. If you've been tracking the explosive growth of large language models, you already know we're hitting a wall, a literal hardware limitation where just calculating the relationships between words is costing a staggering amount of power. So today, we're looking at a solution that bypasses this completely, basically by tossing out a 400-year-old mathematical convention. Let's get into it. We've got a tight agenda for this. First, we'll hit the AI memory bottleneck. Then, smashing the trig wall, followed by the transverse shift, the Cayley-Ferry bridge, and finally, wrap up with a 74x energy revolution. Section 1, the AI memory bottleneck. So here's the core problem as these models scale up to massive context windows, like exceeding 1 million tokens. They hit this severe memory and computational wall in the self-attention mechanism. Now, the industry usually maps this data onto polar coordinates, right? Because the direction of a vector carries way more semantic weight than its length. But they keep slamming into an invisible barrier, and it comes from a Euclidean habit we've held onto for centuries. Look at this setup. Current systems use radial normalization, fixing the radius, or hypotenuse, c to 1. Doing that forces the AI to use continuous irrational curves. It relies on pi, it relies on complex trig. But the new approach, proposed in the Hecate Universale framework, introduces side A normalization. Instead of the radius, we fix the transverse side A to 1. This one simple flip unlocks discrete, rational grids. It's literally the difference between trying to measure a smooth, slippery slope versus just walking up a set of concrete stairs. And this reliance on the old standard, that creates what's called the trig wall. This is a massive computational bottleneck caused by relying on transcendental approximation, like calculating cosine, for attention scores. Because the old way relies on these numbers that go on forever without repeating, the AI has to constantly estimate continuous angles. Doing that over and over just drains metabolic energy, the actual electrical power your hardware burns. And worse, because it's always just an approximation, it causes precision drift. Over long calculations, the AI literally loses its exact orientation. Moving on to Section 2, smashing the trig wall. To completely shatter this wall, we have to rethink the Pythagorean theorem from the ground up. Take a look at this. We all know a squared plus b squared equals c squared, but watch how it simplifies when we fix our transverse constant a to 1. It refactors beautifully into c squared minus b squared equals 1, which then factors out perfectly to c minus b times c plus b equals 1. It leaves us with this incredibly elegant equation where the radial gap and the expansion are perfect reciprocals. No more dealing with messy squares and square roots. We're working with a perfect mathematical seesaw. So we define this radial gap, c minus b, as lens d in this side A manifold. In this new framework, we treat this gap like a physical object. It establishes the fundamental unit of resolution that anchors our computation to a discrete grid. Think of it as the exact locked-in step size of our geometric staircase. It means we never have to guess or approximate our position in space again. Which brings us to Section 3, the transverse shift. Okay, so here's how the shift actually plays out in mechanics. Step 1, we anchor to that transverse constant, a equals 1. Step 2, we transition away from what researchers call the continuous gunk of traditional angles and move into a discrete step using a spiral count algorithm. And step 3, we completely repurpose the continuous polar arc as a rational lattice. So orientation is no longer the smooth, continuous angle calculation. It becomes a rigid, discrete map governed by absolute integer steps. And the geometric evidence for this is just striking. Take a look at this symmetric diamond tile spiral. It brilliantly surfaces the binary power law expansion. Notice the white tiles extending outward along the north, south, east, and west axes. They are perfect squares landing with absolute bit-perfect alignment. Geometrically, this proves we can map rotational space with a discrete grid. You don't need infinite decimal places to figure out where you are. You literally just count the tiles. Let's get into Section 4. The Cayley-Ferry bridge. So, you might be wondering, if we aren't using continuous math, how in the world do we rotate vectors without using pi or arctangent? Well, enter the Cayley-Ferry bridge. Here, we map Pythagorean triples directly onto this grid. Look at the 4-3-5 triangle on the left and the 3-4-5 on the right. This mapping translates spatial rotation into flawless integer-only arithmetic. Because we're anchored to that a=1 standard, we bypass all those messy transcendental calculations. The rotation between these states, it's solved by simple native bit shifts right in the hardware. Think of this mechanism as an ASCII staircase. It completely discards continuous rotation angles. Instead, it treats orientation as a discrete mapping table. Much like how the ASCII character D is perfectly anchored to the decimal integer 100, this system enables bit-perfect clicks between rotational states. You aren't sliding down a slippery, continuous curve anymore. You are stepping firmly from one coordinate to the exact next one. It's forensic, it's totally trackable, and it takes vastly less computational effort. And that leads us to our final point, Section 5, a 74 by energy revolution. So what does replacing complex trigonometry with simple integer shifts actually mean for the hardware running our AI? Well, let's look at the benchmarks on 28-nanometer CMOS hardware. Standard FP16 multiplication, the old Euclidean way, costs 3.7 picojoules of energy per operation. Even dropping to INT8 addition costs 0.1 picojoules. But the side-to-rep reciprocal shift? It drops that energy cost down to an astonishing 0.05 picojoules. By swapping out heavy multiplication for a simple reciprocal shift on a lattice, the energy floor completely collapses. That is the 74x reduction in metabolic energy per scoring operation. Let that sink in for a second. 74 times more efficient. Imagine an AI running perfectly on your phone using just a fraction of a percent of battery, or server farms slashing their power grids down to almost nothing. This is specifically optimized for the new wave of 1-bit and ternary hardware. By perfectly aligning pure mathematics with the physical logic gates of the hardware, we bypass the massive energy tax of spatial approximation entirely. And it's not just about the energy savings either. By staying on this discrete rational lattice, the architecture achieves literally zero precision drift. Look at this. Over 1,000-step simulation, tracking long context attention, legacy systems drifted by a margin of 1.0075, all thanks to those trigonometric rounding errors. But the SIDA setup? It remained perfectly at 0.0000. It absolutely eliminates the errors of traditional approximation. Which leaves us with a profound question to wrap up this explainer. With infinite context windows and zero precision drift costing nearly zero metabolic energy, what boundaries will AI break next? When an AI can perfectly orient itself using a fraction of a picojoule without ever losing precision to trig drift, what limits even remain for infinite context intelligence? By simply shifting our perspective from a continuous curve to a discrete, rational staircase, we might have just unlocked the absolute hardware limits of AI. Thanks for tuning into this explainer. I hope you found this shift as mind-blowing as I do.